So, review session part 2. We've got chapter 6 with stereochemistry. The big things to remember here from this, you've got nomenclature, primarily your R and S. Then you get identifying the relationship between chiral versus achiral compounds, and then your structural relationships. Since I believe I've got slides on the others, let's go ahead and take a look at the chiral versus achiral. Officially, your chiral definition is something that is non-superimposable on, that's a really long word, on its mirror image. Okay. And since that's the official definition, that can be a bit tedious because you'd have to draw out the mirror image each time. So one of the other things that you can do as far as we're concerned in organic chemistry, as far as you're going to get tested on, you can look for technically any atom but a carbon with 4 different groups attached. Okay, or different atoms. Put different in quotes. Remember, different means distinguishable. Can you tell a difference between them? It's not carbon-carbon, but one is a CH2 and the other is a CH3. Those are technically different atoms. So let's go ahead and continue through. When it comes to our nomenclature R and S, we get assigning that based on the Cahn-Ingold-Prelog rules. So you first need to identify your chiral carbon, which we just discussed, finding a carbon atom that has 4 distinguishable groups attached. And then you'll go through and assign a priority number to each group of the chiral carbon. Your priority is assigned according to the atomic number of the atom attached, and 1 being the highest, all the way down to 4 as your lowest priority. If the atoms attached are the same, then you can move 1 atom further away and evaluate. Do they have a different molecular weight? If not, you go back to your starting atom and go back out again. If you still see no difference, then you can continue on through the rest of the structure until you either don't find a difference, in which case there aren't 4 distinguishable groups, or you find a difference and then you can determine based on your priority there. And that priority difference tracks all the way back to your chiral center. Once you've got your priorities assigned, you can go ahead and rotate the molecule so the lowest priority group is aimed away from you, or in the dashed conformation. You can then go through and connect an arrow, or use an arrow to connect the other atoms from highest to lowest priority. If that arrow runs in a clockwise fashion or a clockwise direction, you would assign that chiral center the R, stereochemistry. If it runs counterclockwise, you get the S. Next deal is going through and actually classifying a pair of molecules. So we've gone through this flowchart a few times. It's just a question of applying each time. You will not have the flowchart directly on the exam. If you want to write it on your cheat sheet, that's fine. I would probably recommend not doing that because that's an awful lot of stuff to include on your cheat sheet. Right? This figure is going to take up a lot of space. But that's just my general opinion. Make sure you go through and apply. It might make sense to just go through and identify the big ones, so superimposability and then maybe mirror images. So just kind of make your best decision on what you want to use to identify these things. You will absolutely see questions where you've got to compare these 2 kind of compounds. At that point, we can move down into chapter 3, and that's where we get our alkanes, in particular our cycloalkanes. So that's where we end up with chairs. You are responsible for your nomenclature when it comes to your alkanes. Let's check here real quickly. No summary information given on these slides, sorry, so you'll have to go pull up your notes. With your alkane nomenclature, the big things you remember, you got your meth, eth, prop, bute, bute, pent, and can I fit it? Hex, where we're referring to 6, 5, 4, 3, 2, 1 carbons. I'm not big on the common names, as you're aware of, but if you happen to remember them, that's probably not going to hurt as well. The larger things from this chapter that are probably going to cause more problems would be looking at Newman projections. It's just another way of looking at the same compound. So if we take ethane, and if we draw a Lewis structure, it looks like our bond angles are all 90 degrees, okay, which is not what they actually are in reality. So we could take that a step further and add wedges and dashes to our structure. The hope being that we could then see a better representation of the three-dimensional model. Okay, we got the hydrogen up here, wedge being coming at you, the dash going away. So if that was our structure and we wanted to convert this into a Newman projection, what we'll then want to do is pick a direction to look down. Okay, this structure is a little bit easier because there's really only one bond to look down. So what I'm going to do is go ahead and draw on our little eyeball over here, looking at this down this bond. Our front carbon atom will be a point, and our back carbon atom will be drawn as a circle. So if we go ahead and put this in, what we're going to do is pull this front carbon out towards you. So here's my three-dimensional representation of that atom coming out at you. And there's our carbon in the middle. We've got a hydrogen going directly down in the plane. The hydrogen that was wedged is now on our left-hand side going up away, and the one that was dashed is now on our right-hand side going up as well. We can now track backwards to the carbon in back. That carbon in back, we can't see that bond, but we can see the atom, and we'll show the atom as that larger circle. We've got a hydrogen going up and a hydrogen going down to the left and to the right. And we now have the Newman projection as I've drawn the wedged and dashed format. In this case, you'll notice that we can clearly see all of those bonds. We end up referring to this conformation as the staggered, which I probably spelled wrong. If we up the complexity of the structure, for instance, if we added some carbons or other things like that, which I'll show you in just a second, that would be, we further refine the staggered definition into a couple others. If you're asked to draw all the possible Newman structures for an individual compound, what you have to go through and do is decide which carbon you're going to rotate. And we're going to rotate one of those carbons 60 degrees until we get all the way back to the beginning. Okay, so in this case, I'm going to rotate my front hydrogens, and I'm going to rotate downwards by 60 degrees. If I go ahead and do that, okay, in the process of doing my 60 degrees, my hydrogens are now all there. I'm not touching the back hydrogens, they're not moving, so they're in roughly the same spots. And if we were to try and draw this out, you'll notice that, actually, my fingers are actually doing pretty good here. Those bonds and atoms are now pretty much all overlapping each other. Or, said a little bit more fancily, they're eclipsed, or eclipsing. So what we've got is an eclipsing Newman projection. That would be our next Newman projection. We would then have to rotate our hydrogen again by another 60 degrees, and I will let you go through and test all of those possible Newman projections, and what you'll find is there's only two unique ones. The one we've got here in the eclipsed and the one we've got here in the staggered. Okay? So if we ask you to draw all possible Newman projections, we're asking you to draw all unique Newman projections. And that unique is very critical on the energy of those Newman projections. Okay? So when we look at energy, all eclipsed conformations are higher in energy and all staggered ones are lower in energy. Let's go ahead and change our initial Newman projection. So I'm going to erase all this other structure stuff because I don't want you thinking I'm drawing that now. Come on. And we're going to erase the eclipsed. If, for instance, we had a different structure in here, say butane, okay, we'll look down, in the case of butane, the carbon 2-3 bond. So this carbon up here is going to be carbon number 1, moving to carbon 2, which then moves to carbon 3, and then to carbon 4 in back. this conformation is still staggered, but if we continue to go through and do some Newman projection rotating, we'll find we can get another staggered conformation. Let's rotate the front one because we did so well with that before. We could get this Newman projection, okay, that is also staggered, but it's going to have a different energy than the one in blue. Okay, that different energy is due to the interaction between these two large groups. That interaction we'll refer to as gauche. When we look at it in our original, our two carbons are as far away from each other as possible. They're on opposite sides of our Newman projection. We'll refer to those as anti. Anti is going to be more stable or lower in energy because we've given each group more space or more place to move. The gauche interaction, we've gotten those a lot closer to each other, and because they're closer, they start interacting with each other, and interactions as far as chemistry is concerned always means increasing in energy. Okay, so that's our Newman projections, all our possible deals. The next issue is looking at chair conformations. When we go through and draw chairs, I would usually recommend drawing two roughly parallel lines, or trying to make them as parallel as possible, of equal lengths, but staggered. So then we'll roughly cut the structure in half. We say, okay, I'm now going to pick the shortest line, so on the top one, that's my shortest line, and I'm going to draw my bond outwards. Now that I've got my extra carbon, I can connect. We'll now move to the other half of the structure, and the bottom one is the shortest line, so I'll go ahead and draw in my bond there as well. And now what we've got is our chair conformation. The next issue is deciding what happens to the hydrogens that are around on this chair, or if it's other things, where those other things are. Okay, and we end up with two possible orientations. You can get the up-down orientations, which we will refer to as our axial. Those are going to be the easiest ones to draw. They are literally up and down away from the structure, or they're on the axis of our cyclohexane. The equatorial positions, not quite as easy to draw, so worst case, label it when you draw out your answer. Say this is equatorial, this is axial, and then that way there's no confusion. And as long as you're drawn roughly correct, you'll probably get the points. Officially, your equatorial should be parallel to the second bond away. So if we start at our lower left, there's our equatorial position. If we count out our bonds, 1, 2. It's parallel to that second bond. If we count it the other direction, 1, 2, it's also parallel to that. Okay, so our other equatorial positions, there's one, up here, there's one, then here's one, and here's one, and here's one. Like I was already saying, is the equatorial a little bit trickier. Some of them look like they're aimed up and down, particularly the ones in the middle. Okay, and when it comes to the axial, we always want to draw those up and down with respect to where the triangle points. So if we take a look at our upper right, the triangle is pointing mostly up. If we take a look at this carbon, or that triangle, it's pointing mostly up. So our axial is aimed up with that axis. Our equatorial is anything that's not that axial position. Okay, so as far as stability, your equatorial is the most stable because it has the most things. There's the most space, most free to move around, and it doesn't butt up against anything else. Okay, that interaction is largely seen when we take the Newman projection of the chair. Okay, so what we're going to do is now set up our Newman projection again. Here's our little eyeball peeping in. Okay, so what we're going to look at is down these blue bonds. So I'm going to draw the left of the Newman projection first. The carbon in front has a hydrogen going straight up, one out to the left away from it, and then there's a bond going down to our CH2. Okay, that CH2 is then going to go up to a carbon in front. That's the front of our other Newman projection, You can draw that in, and we can go ahead and continue out the rest of the structure, and you should end up with something along these lines. Deciding axial versus equatorial as far as which one's more stable. So let's go ahead and put in two methyls. Put in a CH3 here. Okay, that CH3, you'll notice, is going up and down. So we're looking at our red one being our axial CH3. Let's put in a green one as our equatorial, and we'll put it in on the other side. We'll still put it on the front carbons though. So there's our CH3 that is now equatorial. Okay, and we want to try and decide which of these is higher or lower in energy. Well, conveniently did not label the rest of those blue atoms as hydrogens, but they're all still technically hydrogens out there. And we could go through and evaluate all of our interactions. Most people will see these interactions, okay, between the methyls and the hydrogens. And they'll say, well, there's nothing out here. Well, it's not technically true, so we'll come back to that. Those methyl-hydrogen interactions are very, very weak, and there's very little we can do about that. So we pretty much set that energy at 0. That's our 0 point, and we just kind of go from there. Okay. So now what we want to do is evaluate what large things are nearby. This group is technically gauche to that CH3. The gauche interaction we said was higher in energy. They're buttoned up against each other. This CH3 is going to want to move away from it as best as it can. Okay? And in that process, you end up doing a chair flip or a ring flip. What happens with the equatorial? What things are near it? Well, if we look around it, we get those hydrogens. The only atom that we can really see would be, again, that back CH2 from our ring, but the relationship there is anti. Okay? It's as far away from it as possible. Okay? So our anti-conformation ends up being, our anti-Newman projection verifies that our equatorial is the lowest in energy. Okay? So you always want to put your groups into the equatorial position. And we're exiting and moving on, which is what I want to do anyway. I'm not sure how much we want to go through on this. In theory, this part should definitely be very, very repetitive. As far as your definitions, most of Chapter 2 is dealing with your Bronsted-Lowry, but it really covered all definitions. We have a Bronsted acid. The main things I want you to get out of this would be an H+ donor. H+ is also more commonly referred to as a proton donor, so I almost always refer to it as a proton donor. A Bronsted base is an H+ acceptor. As we said at the beginning of the semester, that definition is very narrow. So what another chemist came along and did is broadened it and said, you know what, let's not look at hydrogen ions, let's look at the electrons. So Lewis came along and said an acid is an electron acceptor. Okay, well, if we compare this back to Bronsted's definition, we said a Bronsted acid was a proton donor. Well, what does a proton need to stabilize? Electrons. So a proton is effectively an electron acceptor. If we look at the base, perhaps a little bit easier to see, a base is going to be an electron donor. It's sharing electrons with H+, just like up in the Bronsted definition. Okay? These definitions you absolutely need to know and be able to apply. I will test you on this material, both knowing the raw definitions as well as being able to apply them. A couple other terms that have shown up during the semester is the use of the term nucleophiles and electrophiles. They are, for all intents and purposes, the same as your Lewis acid and base definition. An electrophile is electron loving, so it is electron accepting. So we get an electrophile. A nucleophile is nucleus loving. Well, the charge on a nucleus is positive, so our nucleophile must have electrons to donate. So we look at a nucleophile. Okay? So those are your primary issues with your acids and bases. There are some strong acids and bases, or some strong acids that you should remember. HCl, HBr, HI, sulfuric acid, H2SO4, HNO3, nitric acid. Those, while not strictly required to have those memorized, it can help you answer a lot of quick questions along reactivity lines. Okay, the conjugate base of a strong acid, so let's pick a strong acid like HI. If this acts as a strong acid, it's going to give up H plus and I minus. Whoops. The conjugate base, so our negatively charged species, in a strong acid situation is really weak. So this ends up being a weak base. Well, if it acted at base at all, it would react with hydrogen going back to HI, except HI is a strong acid, which by definition dissociates into the ions. So I minus then, by definition, or reverse definition, has to be a weak base. Okay? Some kind of red flag things that we could look for so you can identify these things quicker. If you're going to look for a Bronsted-Lowry acid, the biggest thing you need to be looking for is a hydrogen attached to an electronegative element. Okay, so let's just say HX. So oxygen, halogens, nitrogens. You can see them from carbons, but that tends to be a little bit more rare and requires some secondary effects. Okay, we saw that way back in chapter 13. Okay, for a base, the big thing that you're going to be looking for is it needs to be an H plus acceptor. We need to look for electrons or a negative charge. When we move to Lewis acids, they're electron acceptors. So to accept electrons, we're probably looking for something that's positive. But now we're going to look for something that is not a hydrogen. Most Lewis acids that we deal with in organic chemistry are carbons, but you will also see metals acting as Lewis acids. For instance, if you think back to the EAS mechanism, you had aluminum trichloride and I think it was iron tribromide. Both of those are Lewis acid catalysts. The metal ion in each case can accept electrons from another halogen to make a better electropile. Big red flag for Lewis bases, very similar to the Bronsted bases, you're looking for that negative charge. Okay? Be aware of all of those rules, etc. When we move into chapter 1, this is where we're getting back to atomic structure. You get hybridization, molecular shapes, all of that fun stuff. Okay. I don't remember if I found my slide. Let me skip ahead. Shoot, I did not find my slide. Let's go ahead and try and start that back. I'll learn it. Chapter 1. Okay, so chapter 1 with our hybridization, we're looking for electron groups. Sorry, got to get centralized again. We're looking for our electron groups. Oof. If you have 4 electron groups, we need 4 equivalent orbitals. That's where we get sp3. So we'll take all of our atomic orbitals and turn them into 4 new atomic orbitals. Those new atomic orbitals will be called sp3. If we have 3 electron groups, we have an sp2 hybridization, 2 electron groups, we have sp. So what we're doing is taking the atomic orbitals for each of these and trying to hybridize them into a new situation that explains our three-dimensional structure. When it comes to the three-dimensional structure, you are responsible for knowing pretty much this one section right here. Okay, so the bond angles and those shapes. A tetrahedral structure is one that has 4 electron groups, which would give us sp3 hybridization. Trigonal planar, 3 electron groups, we're looking at sp2 hybridization, and the linear gives us sp hybridization. Okay. In the case of the trigonal planar, we end up not hybridizing a p orbital. That p orbital is what's used to make our pi bond or our double bonds, or triple bonds for that matter, when we move up into our alkenes, alkynes, and our carbonyls. Okay? That's about all I can remember there. Next part, so here I summarized better the number of carbons and what they correspond to. So your 1-metheth-pro-bute. I expect you to be responsible up to hex. Okay, so 6 carbons. You should absolutely know all of those. In theory, at any point in the future, if anybody mentioned any of those, you would be able to immediately know what happened, okay, or how many carbons there were. You're officially responsible for all of these functional groups, knowing some chemistry of every single one of these. Okay, we've evaluated all of them to a much lesser extent. The ethers, we really didn't talk about those much, so that's kind of my fault. But we did talk about all of those other ones. You're responsible for knowing how to name them, their functional or their reactivity, their basic reactivity, and then specific reactivity. What chemicals will cause each of these things to react? Okay, so there's a lot of information stored within that, and you need to be able to apply the definitions from our acid-base chapter to each of those. Yeah. Trying to wrap this up faster. Lewis structure basics. With organic chemistry, we've simplified things a lot. A lot of people seem to be having some trouble with Lewis structures based on me talking with people asking questions. Go back to our very first presentation, because I didn't put the rules in here, and go through the rules that I specified. They are slightly different than you've typically seen. So apply those rules and you should consistently always get the correct Lewis structure every single time. There are some other pieces that you were supposed to pick up from doing all the Lewis structure practice from that chapter. Number 1, we simplify our drawings. Every point within a structure is technically a carbon atom unless we specify otherwise. We'll almost always imply hydrogens, and they will only be implied when attached to carbons. Every other circumstance, we have to show those hydrogens. So you'll always see OHs or NHs. We don't imply those. And we'll add those or have implied hydrogens up to carbon's octet. Okay? And that gets a bit tricky, particularly if the structure gets charged. Which brings us to our next point, and that is that we will never, ever, ever imply charge. Okay? Because if we imply charge and the number of hydrogens, then we can't tell anything about our structure. Okay? So when we're talking about carbon's octet, it needs pretty much 4 groups of electrons or a charge. Okay? So in its neutral state, it has 4 bonds. Those can be double or triple, but it needs 4 individual bonds. If it moves to a positive state, we're looking at 3 bonds. If carbon's negative, again 3 bonds, but now we've taken one of the 4th bonds or the 4th bond and turned it into a lone pair to get our negative charge. Okay, you can see some of the common bonding patterns there for nitrogen and oxygen as well. The last thing, I've always tried to avoid doing this rule, but it almost always happens. Nitrogen, oxygen, and your halogens almost always have implied non-bonding electrons. Okay, so we can imply non-bonding electrons on those atoms just like we can imply hydrogens on carbon. Okay, so be aware if you only see 2 bonds to an oxygen, there are 2 lone pairs matching with it because it needs those 2 lone pairs to balance out its octet. Okay, so watch out for that. Like I said, when I try and write exam questions, unless I'm specifically testing for this rule, I will try my best to make sure all of those lone pairs are there, so you're ready to go with that. Okay? There's your Lewis structure basics. I think we're done. Sorry for the loss there. Back to our very final slide. Resonance and mechanisms. I should have put this a whole lot earlier. Sorry about that. When we're dealing with resonance and mechanisms, we're always trying to find a source of electrons. So our mechanisms are following using curved arrows, and our curved arrows will always start where our electrons are. So the most common source would be lone pairs or pi bonds, and we're going to move them in very particular fashions. We're going to move them towards a place that lacks electrons, so typically a positive charge. When we are dealing with resonance, we'll move those electrons from atom to bond or bond to atom. Okay? If we want to cheat, we can move them from bond to bond. I didn't click next. Piece of junk. So in the process of doing those shifts, as we keep going back and forth, we can only do those very, very short jumps. Okay? If in the process of moving, say from bond to bond, the next atom over now has too many electrons and has a pi bond to move, we can move that pi bond. But it's a new set of electrons. It's never the same set that's jumping. Okay? And that's what's happening in Rule 3 here. So we'll verify that our octet is satisfied. If it's not satisfied, we can either break pi bonds by moving it away, or we leave a formal charge. Okay? One of the more common ones that I've been noticing students leaving out is the bond to atom. A lot of people don't like to put a charge on an individual atom or a negative charge on an atom. That's fine. You're allowed to do that. Show that resonance structure because it is important. It is a contributor to your overall reaction. When we're in mechanisms, you get very similar rules because we're moving electrons. You'll find your source. We'll move the electrons towards our chosen atom. In this case, our source of electrons would have to be a nucleophile, and our chosen atom of where we're moving our electrons towards would be an electrophile. Okay? Once we've done that simple one arrow motion, we'll verify that the octet is satisfied for all atoms involved in that single arrow motion. If the octet is not satisfied, i.e. if we have too many electrons, we will then try and break the easiest bond. The easiest bond is almost always a pi bond, and then you can drop down to sigma. Because that bond that you're breaking has to be taking the electrons with it, it's almost always an electronegative element taking the electrons along with it. Okay? Always, 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 unless you really just don't want any points on the exam or any mechanistic questions, you need to make sure that you move your electrons from a source, a negative, to a positive. Okay? Never, ever, ever move an atom with an arrow. Atoms do not move, only the electrons move. Okay? So you now have an hour and a half, 2 hours of review slides to go through. If you've got questions, please feel free to email me. And for those of you that did not hear, I should be available on Monday on campus. I will post to Canvas what time I will be at Mesa. Okay, it sounds like it'll probably be the evening because I don't want to spend the whole day here. Good luck and have a good night.